We're going to be talking about moving horizon estimation in Simulink. Okay, so moving horizon estimation, it's an estimation method with dynamic data where we're going to be reconciling a model and a measurement. So let's say we have a process, for example, and we have some input to that process that's changing. We also may have some noise. And so the true output, okay, so that is the true value. It is corrupted, or maybe we don't have an exact model of our process. And so what we're going to do is going to take that information in, as well as any measured inputs or disturbances, into our moving horizon estimation, and then out will come parameters or states. Okay, or states similar to what a common filter would be, but we can include constraints, nonlinear models, and there's some other nice things about moving horizon estimation. So we're also so here we just had two parameters, tau and then k, that came out, and then also our estimated output, and we're going to compare that with our measured output right here. So before I start with this, let me just talk a little bit more about moving horizon estimation and the mathematical formulation of what we're going to be solving. So this is related to dynamic modeling and dynamic control. We often have an inaccurate model, and where we don't know all of maybe the inputs, or don't have quite a correct representation of our actual system. But we have a model of the system that we want to correct so that we might be able to use it for optimization or control. So the same inputs are coming in to the actual system, and we're measuring those and putting them into the model of the system, and then we get a simulated output coming out and also a measured output from our actual system. So we want to adjust the parameters and the states of this model of the system so that these two are going to align. So mathematically, that's just that we minimize the difference between the measured values and the model values, and this is going to be some norm. If it's a 1 norm, then it's going to be the absolute value. If it's 2 norm, it's going to be the square, and we take the square root. If it's the infinity norm, then we take the max value. We try to minimize the max value. But it's going to be subject to these either equality or inequality constraints. Okay, so for moving horizon estimation, here are two popular methods for doing that. This one on the left, that's called a squared error. Okay, that's a squared error objective, and then you see the same model equations here and also here. Okay, and this one, we're going to call this one an L1 norm, or it's like you're minimizing an absolute value, but we've added just something else here, which is also a deadband. Okay, so there's the deadband on the upper and lower. You have a couple of these what are called slack variables. Those have to be greater than or equal to 0, but we're essentially trying to minimize the upper and lower error, and then also this is the change from the prior values. And then we've also put a cost on parameter movement. Okay, so cost on parameter movement here on the left. This is a squared penalty from prior model predictions, and here's a squared penalty from the measured values. Now the reason why we put here and here a penalty on movement from prior model predictions is kind of like a forgetting factor. Okay, it's kind of like in a common filter, how much, like the Q and the R matrices, how much you believe the measurements or the model, and it approximates an infinite horizon of measurement. So it includes a little bit of the prior solution in the current solution. Okay, so then the other thing that we're going to be showing in this video is not just moving horizon estimation, but also how moving horizon estimation might interface with a model predictive controller. So in some cases, this is just the output that we want, just parameters or states. But in many cases, we actually want to do something with those parameters and states. And so we might be feeding those to another application, which in this case is a model predictive controller, where we're saying what we want the set point to be. Okay, that's going to be coming into the MPC this way. Okay, but these might be parameters and states that from our corrected model. So we've corrected this thing that's inside here, this model for the model predictive controller, and then we get better manipulated variable moves that then come into the actual process. Okay, now we still might have that same noise, you know, from measurement noise or inaccuracies of our model, and then that will come down here into our MHE along with this measured input, and it will correct the model and then send it over here to the model predictive controller. So let's just go and download these examples right here. So what I'm going to do is go ahead and open up a web browser. If you just go to APMonitor.com/DO for dynamic optimization. So this is the course on dynamic optimization, and we're going to go down here to the biasing EKF and UKF link, and so this is kind of an introduction to estimation with some of these examples. Okay, so first of all, let's just go ahead and download this MHE in Simulink. I'll go ahead and save it to my desktop. It's a zip file, and make sure you extract it right after you get it. Okay, so I've extracted it, and now I'm going to work with the unzipped folder. Okay, so I'm just going to go ahead and open up MHE Simulink. And so as this is opening, let's just go back to this statement. We want to implement MHE without model predictive control. Understand the difference between tracking performance, so green between model and measure values, versus predictive performance, model parameters that predict into the future. So here is our MHE, and okay, so the same thing that we just reviewed, but what I want to do is just step through some of the code so you can see what's coming in and what's leaving. This is just going to be a pulse generator, so my manipulated variable, my U value, I'm just going to be manually pulsing that up and down. It's going to go through the process. There's going to be some noise that's added to it, and then that's going to go to the moving horizon estimator. And then we'll watch the measured and estimated outputs. Okay, so let me also just put a breakpoint in here on the MHE function. So this is the moving horizon estimation function, and I'll just put a breakpoint right here near the beginning. Okay. Okay, so there is my breakpoint, and then let me go ahead and run this. I'll run this application. Okay, so the first thing that's going to happen is it's going to hit that breakpoint right there, and I have some persistent variables defined. Okay, it's just empty right now, so because it's not defined. So if it's empty, then I'm going to visit this initialization phase right here and just initialize my moving horizon estimator. Okay, so I'll go ahead and step in. There's my server application name, and you know, I think I'm just going to go ahead and step out of that. Okay, so what I have is okay, so sorry about that. So we're going to first of all initialize this MHE, and I'm going to go ahead and step into that. So first of all, I'm going to add a path to that APM folder. That's the APMonitor just libraries, and I'm just going to go ahead and step through this. I'm going to first of all clear any prior application that was there. I'm going to load this model and load the data file. So let me go ahead and open up those. So this was my my model, where I have a K, a gain, a tau, a time constant, U is my input, and Y is my output, and then I have just one equation right here. Okay, and then my data file, I'm just going to open this up with Notepad. I just have my time horizon. Those are all the points that I want it to solve at. Okay, and then we come back here. I select iMode 5 for moving horizon estimation. Okay, and then nodes. That's how many collocation nodes I want per time step. And then I also have my web plot frequency. It's going to update my plots on my web viewer every 1 second. Now I'm going to classify a couple of these variables, my k and my tau. I'm going to classify those as parameters. They're going to be constant over the horizon. Those are FVs, or fixed values. I have manipulated variables, u, that can vary over the horizon, but I'm going to have input that into the MHE. I have my y values that are my measured outputs. And then I'm going to turn my k status on. That's going to make it a degree of freedom for the optimizer. I have my tau status. That's also a degree of freedom for the optimizer. My u status, that's going to be off. So I'm going to be measuring it, but I'm not going to be changing it. Okay, I set my d cost. That's my delta cost. That was a parameter in my objective function. How much do I want to penalize the movement of k, and then also of tau. Dmax is how much it can move every cycle. So that's a delta maximum that the k and the tau can move. Then here is my feedback status, or which ones are measured. So I'm not measuring k and tau, but I am measuring u and y. Okay, and then I'm going to return successful initialization, and that's going to go back to the other function. So that's only going to visit this initialization step just once, right at the beginning. Now what I have is essentially these next 4 are just going to be inputting the measurements that I got. So let me go back to the Simulink. Okay, so I had 2 measurements. The first one is going to be my, in this case, it's my measured output, and my second one is that u value. Okay, so that's going to be coming into my moving horizon estimation. I just combined those 2 signals. Okay, so the first one is y. I'll go ahead and step, and then u, and then put those in with the APMonitor.com function. That's a measured values that it's putting in to the model, and then I'm going to go ahead and solve it. Okay, and then it's going to solve, and then I'm going to retrieve the solution, and then I'll go and get the k value, the tau value, and the y prediction. I want to take those from the end of the horizon because that's the current time. Okay, then I have outputs k, tau, and then y prediction. So if it's the first time through, then I'm going to open up a web viewer. Okay, so it's going to pop open a web viewer, and then let's just look at it here. Here's my first prediction. I only had 1 measurement, so it just came in and it matched up just that 1 measurement. We'll see that start to fill in later as we go through more of these cycles. Okay, so I'm going to go ahead and just select continue, and it's going to go back to this same point. And then if I step now, it's going to skip that initialization, just input the measurements, and then solve it, and there's my solution, and get my k, my tau, my y prediction. Those go as outputs, and then goes and doesn't open up another web viewer. Okay, and then I'll just go ahead and continue, and I'll hit continue 4 or 5 times just to see this thing go. Okay, and then let me go back to my web viewer now. Okay, so you can see I'm starting to get some measurements in, and I have model prediction. Let's just look at my u value. So it did step to a new value. And let's look at my k and my tau values. So my tau value started here at about 7. If I click this, it's going to go full screen for me. Okay, and you can see it went up to about 27, 26. Okay, the true value, let's go back to see what the true value is. So we want this to start estimating, the gain is 5 right up here on the upper left in the process, and the time constant is 10. So that's going to be the true value. But there's some initial mismatch. We had a bad guess for tau and gain, and so it's going to try to find that as we start cycling through this moving horizon estimation. Okay, so I'm going to do it for a few more cycles. Just keep clicking continue a few more times, and then let's go back to our web viewer. Okay, now here the tau value is starting to drop a little bit. Let's see about the k value. Okay, so that's dropping. Let's see how well it's predicting these. Okay, so it's doing a very good job right now, but we still don't have a really good estimate for k and tau yet. So I'm just going to take away this breakpoint now, and let's just watch it as it goes. I'm going to go ahead and go back to my editor and just remove that breakpoint and select continue. Okay, and if I come here, I can see my y value. Okay, so it's tracking fairly well. I can see my tau value, and that has converged to a value of about 10. And let's go to my k value as well. This is my gain. Okay, so it should go to about a value of 5. Okay, it is fluctuating a little bit, but I think it's doing a fairly good job. If you see this error, it just means it was trying to write the plot at the same time as reading it. There we go. So there's the moving horizon estimation. It's doing a very good job matching up over the horizon. And you can see some of the U values that were input. Okay, so just some steps that were coming in. Okay, so so great. It produces k and tau values. One of the important things that we want to visit, though, is how this affects model predictive controllers, though. So in this next example, what we're going to do is just download this MHE and MPC in Simulink, and now these MHE parameters are going to be going into the model predictive controller. And then, so I'm going to go ahead and close out this example in Simulink, and I'll close my MATLAB. Okay, and I'll go ahead, just make sure you unzip this first, extract it before you start using it, and then I'll go ahead and open up MATLAB. Okay, so let's see how the MPC controller does with linked up with a moving horizon estimator. So we want to obtain parameters so that we can get the best performance possible out of this MPC controller. Okay, and just initially, let's see what our initial guess is for our model. We have k of 5 and tau of 10. Okay, now let's go ahead and change those in our actual system. So I'm going to go back to my moving horizon estimation, and let me just change this to a gain, let's say of 2, and a time constant, let's say that is 5. Okay, so different than what the MHE or the MPC have. And let's see how the MHE and MPC do this. Set point, I'm just going to have that going up and down, amplitude of 10, period of 50 seconds. So it's going to go through a couple steps in our 100-second simulation. Okay, so when I click run, it's going to bring up 2 web viewers in this case, one for the MHE and one for the MPC. Okay, so this is the second one is the MPC. Okay, so there's my desired target, and you can see the model and the measured values. Okay, so there is a little bit of model mismatch, but overall the MPC and the MHE are doing a fairly good job of tracking. Right there you can see, it's trying to figure out right in the beginning what the K and the tau are, but then you can see it's able to figure that out, and we get very good performance here, leading to acceptable control for our model predictive controller. Okay, so that concludes this tutorial, just keep in mind that let me go back here, that model predictive control and MHE, when you have an MHE alone, you can tune that to get acceptable predictions, measured versus estimated outputs. But when you have a model predictive controller, you've got to maybe tune it just a little bit differently so that those parameters that you feed to the MPC are able to predict very well over a long future time. So this exercise was just to get you to think a little bit about that, about how to tune a moving horizon estimator to be able to give acceptable parameters that can predict well into the future for a model predictive controller.